ladies and gentlemen. This is the review video for the fundamentals of molarity. This video should help with some of the questions on the review assignment. It's not getting into too much of the specifics, just getting at the definition of molarity and some very common types of problems we see. Up first, the formula for molarity. Molarity is the most common unit for concentration in chemistry because it deals directly with the mole. There are many other units for concentration, but those tend to use grams or perhaps the weight of the solution, and while they certainly have their place, they're not quite as useful as molarity, which is defined as moles of solute per liters of solution. Molarity, if you don't remember from Regents, the abbreviation for molarity is a capital M, so when you're labeling the unit of the concentration for molarity, you put a big capital M right after the number. The key thing to remember with the molarity formula, or as I like to call it simply the molarity unit, is that it's key here that it's moles of solute and liters of solution. And the reason that I mention that and really make a point of that, despite the fact that the formula is already there, is because of this bullet point right here. You will very, very frequently be given volumes of solutions that are in milliliters, because it's a much easier unit for you to actually go into the lab and measure. If you think of a 100 milliliter graduated cylinder, a very, very common piece of glassware, it's not called a 0.1 liter graduated cylinder, it's called a 100 milliliter graduated cylinder. So you need to be aware of the fact that you're most likely going to be given volume and molarity problem in the wrong unit, and that if you need to calculate molarity, you're going to need liters of solution. So a little bit of a reminder right here that 1,000 milliliters is equal to 1 liter. That milli prefix means 1,000 times smaller than the base unit. And it is very likely that you will have to convert units that you're given in the beginning part of the problem to get, before you plug it into the molarity formula, in order to correctly calculate molarity. You are not calculating molarity correctly if you use milliliters in the denominator in your calculations. So first up, a sample problem. What is the molarity of a 652 ml solution containing 0.388 moles of Na2CO3, sodium carbonate? Well, we're asked to calculate molarity, and molarity is defined as moles of solute per liter of solution, and we look at the information that's provided in the problem. We have volume of the solution. It does specify that that 652 milliliters is for the entire solution. So we have that information, and then it says that we have that number of moles of solute. So moles are a check. That's the 0.388. And liters, well, we don't have liters precisely, but we do somewhat have them. We're going to get this from the 652 milliliters. So just a reminder, if you want to do a quick T-chart, in 1 liter there are 1,000 milliliters. So 652 mils is 0.652 liters. In this class, you are going to get really good at going from milliliters to liters and back in your head. And this isn't typically a step that I'll require that you show. If you want to jump straight to the 0.652 liters, that is perfectly acceptable with me, because this is a conversion we're going to be doing a lot of throughout the year. So this is the value that we're going to plug in on the bottom now. So molarity, moles per liter, so we're going to do 0.388 moles of solute divided by the 0.652 liters of solution, and you just punch that into your calculator, and you get, taking it to the correct number of sig figs, each of these measurements that we begin with has 3 significant figures, 0.595, and the unit, capital M, 0.595 molar. So it's a 0.595 molar solution of sodium carbonate. And another example. How many grams of sodium hydroxide are necessary to make 500 milliliters of a 0.100 molar sodium hydroxide solution? Well, this question, when we read it, when I see this, I zero in on a few things. First of all, I see the fact that the problem has given me volume. It's right there. Volume is provided. I then see that it has also told me molarity. And immediately in my head, I say, Problem told me molarity, problem told me volume. I'm going to use this formula because it has given me two of those three things. And I look back and I read the original question, how many grams of NaOH? That's what we're looking for, grams of NaOH. The molarity formula is not for calculating grams. However, again, if we look at the information that we're provided, we're given molarity. We're not given liters directly, but we are given liters indirectly, which means that we can solve for moles and then convert moles to grams. The way that we convert moles to grams in chemistry, GFM. This type of question right here, in my opinion, I do not see this as a complicated question. I see this as a very straightforward, fairly standard question. At the beginning of the year, it might seem a little bit more involved, but the more types of problems like this that we do, hopefully you're going to feel very comfortable with this sort of a question. So this is our kind of our roadmap. We're going to take the molarity formula. We were given molarity. We were indirectly given volume. We need to convert a little bit to get liters. We're going to get moles of NaOH from the molarity formula. Then once we have moles, we're going to convert moles to grams using the gram formula mass and answer the question. So the 500 milliliters, I'm just going to go straight and say that this is 0.5 liters. 0.5 liters, 500 mils, that's half of a liter. Right, because a liter is 1,000 milliliters. So I'm plugging that stuff in. I've got 0.1 molar equals X moles over 0.5 liters. So that means that I have 0.05 moles of NaOH. That's great. That's not what the problem is asking for. The problem is asking for grams of NaOH. So I am now going to convert that using its gram formula mass. So 1 sodium, which is 23, 1 oxygen, which is 16, 1 hydrogen, which is 1. The gram formula mass of sodium hydroxide is 40. I have 0.05 moles of it, so 0.05 moles of NaOH times 40 grams per 1 mole, I get 2 grams, and if we're taking this out to the correct number of sig figs, I'm going to need 3 of them here because there is a decimal point with the 500 milliliters, 500 point, so they are making the point that it is significant to that extent, so 2.00 grams of NaOH. This is a very useful skill. This particular type of problem is extraordinarily common because you know that you want a 0.1 molar solution. That's your ideal, that's the concentration that you need in order to do the experiment. And you know that you need 500 milliliters of it. So you just need to figure out how much NaOH are you going to put in your container so that you get the 500 mils of the 0.1 molar solution. So this is an extraordinarily common type of calculation. You use the concentration that you want and the volume that you want to get the moles, and then because we don't have a balance that actually measures moles, but we do have a balance that measures mass, you then take the moles, turn it into mass using the gram formula mass of the compound in question. So that's the fundamentals of molarity, and refer to this throughout the year. If you have any question regarding the molarity unit, because we're going to be seeing this in many different chapters in our continuing essentially in our discussion of chemistry.